pressure. So our speaker is a little bit late. So it does seem that the people who have the closest to come, like he's a Willamette professor, usually tend to be the latest. So we'll wait for him. I'll try to keep you entertained for a minute or two. So the topic today is chaos theory. So let's see. So there were three people. There was a doctor, an engineer, and a politician. And they're debating, which was the first profession. And the doctor says, well, God, pulled a rib out of Adam to make Eve, so he was obviously a surgeon, so surgeon was the first profession. And the engineer says, well, no, because, God created order out of chaos, so he must have been an engineer. And the politician says, yeah, but who created the chaos? And the other one that I got, the other one is the bunch of cows in the barn. They're at the milking station, and they break free from their milking stations and go wreaking havoc through the barn and the farmyard. So what did you call that? Utter chaos. It's a dad joke, what the heck. Okay, so we'll still wait for him a little longer here. Hopefully he does show up today. The speaker today, he's going to create some chaos here for us. The speaker today will be a Willamette professor, Dr. Daniel Borrero. He is an associate professor of physics here at Willamette University. He had received his bachelor's in physics from the University of Texas and earned his PhD from Georgia Tech. He taught at Reed College before he came to Willamette, and I think he's been here, if he were here he could correct me, but I think he's been here since about 2006 or something like that. So approximately 15, 20 years that he's been a professor at Willamette. He researches fluid systems with complex spatiotemporal dynamics. You all know what that is? Okay, well. As well as emergent phenomenon, such as spontaneous synchronization in mechanical systems. So, basically that's a long way of saying, chaos theory. So he does study chaos. So when he gets here, he will talk about chaos. We have had him before several times. He is a great speaker, a great science communicator, as are a lot of the people that, have talked to us on science in recent years. So I wish I could say welcome, Daniel, but we're still waiting for him. So I can't keep you entertained anymore. Spontaneous synchronization in mechanical systems. So, anybody have anything fun to say? Anybody have a joke to tell? You do? You have a joke? Great, come for it. Go for it.
One day, unlikely as it seems, a snail was riding on a tortoise's back. And what did the snail say? Whee! My mother loved that because she said it was the only clean joke she'd ever heard.
This is Solveig. I think you have to be Scandinavian to get this, but Ole and Lena jokes, there are a lot of them, and some of them are clean. Ole wants to be a garbage man because that way he'd only have to work on Thursday. And Ole and Lena set off, okay, that's it. Set off to drive up to Minneapolis. They lived in Omaha, and they'd been going for quite a long time when they saw a sign that said, Minneapolis, left. So they went back home.
And I have one more spin-off, another spin-off joke. Kind of similar to the other one, but let's see if you can guess this. So a bunch of marine animals escaped from the zoo. What did they call it? Otter chaos.
This gets better and better.
Okay, well, our speaker is here, so he's getting set up with his laptop, so we'll start in just a minute or two.
Yeah. Do you have anything, any videos or anything?
There's a couple of videos that should be embedded in there, but is there a mouse? Because I do need to click on. Oh, here we go. Yeah, looks fine. Alrighty, cool. All right, sorry I'm late, folks. Traffic was a little bad leaving Portland. But anyway, I'm Professor Borrero. I've seen a lot of you before. I've been here before. But if you haven't seen me before, well, hope you have fun. So today I wanted to talk a little bit about my area of research, which involves what you all were alive in the 90s. You heard about chaos theory. I tell my students, have you heard about chaos theory? And they're like, what? And I'm like, oh no. But anyway, I wanted to give you a little quick sort of introduction to chaos theory. And when I was preparing this talk, I actually realized I was going to get really mathy and kind of dense. So I'm going to do a little switcheroo. We're going to do one lecture on chaos, and then we're going to go full 90s and do a different lecture that's related on fractals. All right? Cool. All right. So I see our friend Bugs Bunny here. As we'll see, our introduction to chaos is really going to be talking about rabbits and rabbit populations. Okay? Okay. So let's start with a model of, let's start talking about a model of rabbit populations. You know, rabbits are sort of well known to reproduce a lot, right? And we could imagine that there is Mama Bunny and Papa Bunny, and they love each other very much. And then after 1 year, the stork brings baby rabbits, right? And so in year 2, our rabbit population is now 4 rabbits, right? And let's ignore the inbreeding kind of implications here, but then these rabbits also love each other very much, right? And so in year 3, how many rabbits do we have? Well, 8, right? Assuming that at least on average, each generation of rabbits has 2 rabbits per every 2 rabbits that you have, right? What about the next year? 16, right? And we can keep going, right? We get 32, and then we could keep doing this n times, right? So at some point we get to a population which we'll call P sub n, which is the population at the nth generation, right? Okay, so far so good, right? Not hard. Okay, so let's go ahead and try to math this up a little bit. Okay, so here's our table. Here's our scenario. We started in generation 0, had 2 rabbits. Generation 1 had 4 rabbits. Generation 2 had 8 rabbits, and so on, right? Can we predict how many rabbits we're going to have after n generations? So I want you to sort of think about what the pattern is and see if you can come up with a method. You don't actually have to come up with the numbers for predicting what the population will be after 10 generations or after 100 generations and so forth. So take a minute and chat with your friends and see if you can. All right, let's see. Did anybody come up with anything they like? No? Yeah, over there.
Yeah, it's 2 to the power of n minus 1.
Okay, that could be it, right. So let's check it out. So we have that the population of the nth generation is going to be sort of, you start off with 2, right? And then you multiply that by 2, and then you multiply that by 2, you multiply that by 2, and that by 2, right? And we have to do it n plus 1 times because there's an extra 2 at the beginning for the 0th generation, right? Okay, so basically our nth generation is given by 2 to the n plus 1, okay? Keeping in mind that one of those 2's, the plus 1 part, is that initial population. Okay, so that's scenario 1. Let's do a harder one. Scenario 2, what if we start with 500 rabbits? So we have 500 rabbits, they each have 2 rabbits, so now we end up with 1,000 rabbits. Those have 2 rabbits, and so we have 2,000 rabbits. We kind of keep going that way. What would the population be at the nth generation? Or how would you have to model, or modify this equation here to get that one? Well, take a second to chat about it. Come up with an answer. Okay, does anybody have anything they like, they came up with? Oh, not the actual, we don't need the actual number, like how would we, or I guess I didn't ask you for a number. How would we change the formula? It's pretty much the same formula, right? We just need to change the initial number of rabbits. So really what it looks like is like 500 times 2 times 2 times 2 times 2 times 2 n times. And so if we do it for n, then it's 500 times 2 to the n, right? Okay, so now more generally, of course, the rabbits could have on average more than 2 rabbits, right? It could be 3, it could be 7, it could be whatever. So we'll replace that 2 with a little reproduction rate, which we'll call little r, okay? And then we could have 500 rabbits to start off. We could have 1,024 rabbits. We could have 1,272 rabbits. We could have 42 rabbits, right? And so that initial population we'll call P0. And then basically we just need to take P0, multiply it by R n times, and that's going to give us our population at generation n, right? Any questions about that? Okay, so the idea is we take the initial population, P0, then we multiply it by the number of rabbits that we have that are born for each pair of rabbits, right? Once for the first year, then multiply that resulting number by R for the second year, multiply that resulting number by R for the third year, and so forth. Okay, so that's going to be our equation for the population of rabbits in generation n. All right, any questions? Yeah? Well, so it kind of gets yeah, that kind of actually gets wrapped up into our R, because you could imagine that if 3 are born but 1 dies, then the net gain in each generation is 2, right? So we can kind of wrap that up into our factor R in the sense that on average, the population increases by a factor of 2 between, or whatever number we want, between generations, even though some rabbits might be dying off in the process. So that's a valid concern though, right? And I didn't explain that, so that's a great question. Okay, any other questions? All right, so let's play with our little model here. And here it's going to get a little bit wordy in math, but basically we're just going to be saying the same thing that I just told you, right? So this turns out to be an example of an iterated map. We can formulate this model as what's called an iterated map. And an iterated map basically just means you have some number, you do some operation on it, call that f, right? So in our case it's multiply it by r. So and then that's your result. And then the next time you take the result from your first calculation, you plug it into the same equation again, right? So basically, in our case, we multiply by r again. So if we look down here, and actually let me turn on the little laser pointer thingy. Okay, so basically what we're doing is, suppose we start off with like 500 rabbits, then we multiply by 2. That gives us the population at the next iteration, right? And then we take that result, which was 1,000, right? And then we can plug it in again, and we can keep going back and forth. Sorry. Okay. Does that more or less make sense? Okay. So in math, in applied math, this is called an iterated map. Okay. Okay. And so if we put our whole result in or all our results for an initial population of 500 in a table, the 0th generation, we start off with 500. Once we apply our function, which would just multiply by 2, we get 1,000. And then we use that as our input for the next step. 1,000 multiplied by 2, we get 2,000. Use that as the input for the next step. 2,000 multiplied by 2, we get 4,000, and so forth. Okay? All right, so that's all an iterated map is we're just taking one result and then plugging it into our function, and then taking the result and then plugging it into the function, right? So, well, you all have played with calculators. I'm sure you can do that on a calculator, right? You hit like ×2 and then equals, and it will just keep multiplying by 2. Anyway, so that's all that we're doing. Okay. So let's go back to our rabbits, right? We went a little math detour. And so let's see what our model predicts. So generation 2, or 1, generation 2, generation 3, generation 4, 5, 6, 7. Oh no, I don't know why the text got copied. But anyway, anybody see any issues with this model? What happens if I keep going? Overpopulation, right? There's basically, this isn't realistic. You can't just have an infinite number of rabbits, right? At least not if we have infinite resources in land, right? At some point they will like get so close together to form like a rabbit black hole, or I don't know, something, right? So this model is kind of broken. Like, it's okay for the first few generations, but eventually this cannot work, right? Okay, so let's see how we can fix this. Any ideas? Huh? Hawks. Yeah, we could add predators, right? That would be one thing. But suppose we're on some island where there's no predators, because then the math gets way harder. Yeah.
We could change the letters in our equation from P0 Rn to some other letters, because if you give rabbits corn, they make
I don't know if I should repeat that. Okay, any other ideas?
Yeah.
I heard a yeah.
Yeah.
Oh, death? Okay, yeah, basically at some point we do need to sort of think about maybe not all of the baby rabbits are going to survive in every generation, right? Like the reproduction rate has to go down once the population gets large enough, right? This is sort of the overcrowding problem, or you know, yeah, it was big in the 90s too, right? We were talking about overpopulation on the planet Earth and whether we could provide enough food for everybody, right? So that's what we're going to do. We're going to modify our reproduction rate in such a way that as the population gets bigger, the reproduction rate drops, right? And that's just going to be taking into account competition between the rabbits once you have finite resources. Okay, so let's go ahead and do that in sort of the simplest way possible. And what we're going to do is we're going to say, well, let's call the actual reproduction rate at any given population big R. We still have our initial reproduction rate, which is what the reproduction rate would be if there's no competition and infinite resources, right? And we're going to say big R is basically just the infinite resources reproduction rate if the population is small, right, or almost zero, right? So if we have 2 rabbits, yeah, they can produce 2 rabbits. If we have 4 rabbits, they can produce 8 rabbits. But if you have 1 million rabbits, they can't produce 2 million rabbits. They might need to produce fewer rabbits, right? So we're going to require that big R be almost equal to a little r if the populations are small. Now, if the population gets really big, we basically say the new offspring just all die because there's no food, right? or sufficient numbers of the adults die so that because there's no food, whatever it is. But basically, the number of rabbits doesn't increase, right? Basically, they're eating grass as fast as it comes up, right? And so what we're going to say then is that R, big R, is going to be 0 if the population is large, right? Okay. And if we're somewhere between like the resources are being all used up or there's infinite resources, then big R should be something in between basically little r and 0. Okay. Well, now the simplest way to do that is to just assume that the relationship is linear, right? So basically big R, starts off at little r when the population is 0. I should have put a 0 here. And then it decreases as the population increases until we get to some population at which we can no longer reproduce, right? And so we're going to call that population K, the carrying capacity. And that's sort of a technical term from biology, right? And in fact, also back in the 90s and the 80s when we were talking about overpopulation of humans, right, people talked about the carrying capacity of the planet Earth and how many humans it could actually feed or sustain, right? So carrying capacity is the maximum population that we can have before we run out of resources, and basically we can't add to the population anymore. Okay, I'm going to take a minute there. Any questions about this chart?
And have them yell.
Okay.
Oh, okay.
Yeah. No questions? Everyone good? Goodish? Okay. So don't worry. Like if you're not following the math, it's not the end of the world. We'll play with this model later, and you can just play with it, and it's pretty fun. So all right. Okay. So mathematically, and this is some trauma from high school. It turns out that you can write this line in this way. So R is just the base reproduction rate times 1 minus P divided by the carrying capacity. So let's see if this works, right? So if the population is 0, right, if that's 0, then basically that term is 0, and so we get R times, sorry, this is really jumpy, R times 1. That tells me that big R is equal to little r when the population is 0, right? On the other hand, if the population is equal to the carrying capacity, so P equals K, I have K over K, that gives me 1. 1 minus 1 is 0, so 0 times R is 0. So the reproduction rate goes to 0 when the population goes to K. Okay? Now we can just plug it into our original iterative map, but now with this adjustable reproduction rate. And our iterative map becomes this. It tells us that the population at the nth plus 1 generation is just the reproduction rate, now this adjustable one, times the current population. And so now I just plug in that equation from above for big R, and I get that P sub n sub 1 is equal to little r times 1 minus P sub n divided by K times P sub n, right? So basically, the population of the next generation is going to be the base, sort of the infinite resources reproduction rate times 1 minus the population now divided by the carrying capacity times the current population. All right, that was a lot of math. But it turns out this is a famous equation. It's called the logistic map. And when biology, population ecologists talk about modeling populations this way, they talk about logistic models. We'll call this the logistic map. Now, the logistic map was actually introduced back in the 60s by Edward Lorenz, who actually wasn't doing biology at all. He was actually doing climate modeling. So it turns out this exact same equation comes up in a lot of different contexts. But Lorenz is sort of more famous for the Lorenz attractor and also a big sort of starting off the field of chaos theory. Although there's a lot of work that was done before him, but he's sort of credited as the father of chaos theory. I never met Lorenz before he passed, but you literally cannot find a picture of this man that he doesn't have that like great smile, and so everything I've read about him, he was the really kind of jolly great guy and super attentive to his grad students and people that were helping him. But when Lorentz introduces the logistic map, it kind of stays buried in the meteorology literature, and nobody really kind of pays attention to it. But it's kind of rediscovered by biologist Robert May, and he's a mathematical biologist, so he talks about mathematical models of, for example, populations, right? And he kind of rediscovers it and reintroduces it. And a lot of the stuff that I'm going to be talking to you about in a paper in Nature in 1976. And so there's a picture of Robert May, who passed during the COVID pandemic. Okay, now, as we'll see in a second, all this work that I'm going to talk to you about really kind of makes sense that it gets discovered and takes off in the 60s and 70s. And the reason for that is that doing these types of calculations gets really, really tedious when you're talking about the 900th and 72nd generation, right? Imagine plugging in 972 times, right? It's not a hard thing to do. Like if you sat with a calculator, you could probably do it, right? But that seems kind of tedious, right? So what happens in the 60s and 70s that makes doing very simple repetitive things a bazillion times very easy? Computers come around, right? And so Lorentz turns out is one of the first scientists anywhere, he's at MIT, to have a computer of his own in his own research group. And this is the monster that he has. So he has this LGP30 computer, which is a monster, right? You have to program this thing directly in ones and zeros. I imagine some of you did punch cards back in the day. By my time, we used them as little shims when we were using in the machine shop. So there was like stacks of data from the astronomy department, and we would just use them to like shim or like protect pieces from getting marred by vices and stuff. But anyway, you all know the concept of punch cards, right? So basically you have to do these punch cards, but this is very early on, so you don't really even have languages. You're kind of doing everything in ones and zeros. This machine turns out to be the first one that explicitly has multiplication built into it. You don't have to write your own multiplication code to then do your multiplication. So, I mean, go nuts, right? Like you can multiply things now. It has a whole 113 vacuum tubes worth of computing power, right? And it has 15 kilobytes of memory. It's stored in these big magnetic drums, and it takes 2 milliseconds to access 1 bit of data, right? So if you want to read 1,000 ones and zeros, you have to wait a whole second, right? And that's not even a kilobyte that you're reading at that point, right? And you only have 15 kilobytes total anyway, right? Now, if we compare that to sort of a modern iPhone has 20 billion, that's 20 with 9 zeros after it, 20 billion transistors in it. So that would be the equivalent of the 113 vacuum tubes. And it has 12 gigabytes, right? So 1 gigabyte has, roughly speaking, 1 million kilobytes, right? And we have 12 of those of memory. And to access a 1 or a 0 takes somewhere on the order of 10 to 15 nanoseconds. That's billionths of a second, as opposed to thousandths of a second, right? So basically, you can access a 1 or a 0 a million times faster, right? Clearly, this is a very, very limited machine, and it's very clunky, and the whole programming in ones and zeros is not really necessarily what your professor of meteorology at Lorentz wants to do all day, right? Who do you think actually did the work? So it turns out Lorentz actually had 2 women that worked for him. One was called Ellen Fetter, and the other one was called Margaret Hamilton. And as we see, once he actually writes the papers, he's actually acknowledges them. There's a very nice article in Quantum magazine called "The Hidden Heroines of Chaos," which talks about these women and their lives. But they're the ones that are actually doing the computations, right? Obviously, Lorentz does a lot of the theory work and try to understand what's going on, but these women are really the ones that do the computation, right? Federer gets married and kind of drops off the face of the earth. Well, I'm sure she had a great life and great kids and everything, but she doesn't really kind of stay in science. Hamilton, on the other hand, when she leaves Lawrence, she actually goes and works for NASA, and she's the person that wrote pretty much all the code that controlled the Apollo landers during the Apollo program. So that's her with her stack of code, and she becomes a very prominent, so that's all like pages of printed out code. That's the code for the Apollo program right there, for the lander. And so she goes on and she becomes a pretty famous computer scientist. Anyway, that was a little aside. So let's go back to our discussion of chaos, right? Okay, so remember we said that our equation looks something like this. I can multiply everything out, and what I'm going to get is something like this. So it's some number, little r, times a variable minus some other number times a variable squared. Now, if you dig deep and you go back to your sort of high school days, you'll recognize that this is a quadratic equation. And a quadratic equation, when you plot it, looks like a parabola. Okay? And a parabola is a graph that looks like this. Okay? So let's see what we were plotting here, right? We're saying for a given population, and sorry, the mouse is not super smooth. For a given population, let's say here, right? What will the population be at some later time? All I do is I follow up here, and then I can read off the graph from here what that value is, right? So this graph just encodes, given the population now, what's the population going to be later? Okay? And by the way, notice that if I start at population 0, I just get population 0. Does that make sense? Yeah, right? No rabbits, no more rabbits. And then if the population is k, right, then, and this sort of sets the max on when I can reproduce, right? Like yeah, okay. So that's our graph. And for sort of aesthetic reasons almost, let's measure everything in units of k, right? So basically we'll say that that this point on the graph is 1, right? 1k, 1 times k. And everything in between is sort of some fraction of k. Right? And the nice thing about that is that it gets us away from having sort of 2 variables here, right, to just 1 variable there, which is just a reproduction rate. And so now we're saying, like, if the carrying capacity is 1 million, then P is measured in millions, right? So a P of 0.5 is 500,000, a P of 0.25 is 250,000, a P of 0.8 is 800,000, right? Okay, so that just cleans things up a little bit, and it'll make it easier when we actually try working with this model. How am I doing on time? Let's see, make sure we get to the fun part. Okay, okay, so I have to hurry up. So what we're going to do is we're going to use an interactive tool to study the behavior of this iterative map. Okay, so before we do that, let's make some predictions. Okay. So suppose that the reproduction rate is small, so that on average, a pair of rabbits only has 1 baby, for example, in their lifetime. What would we expect to happen to the overall population? Sorry, it will go down, and eventually, the last rabbit dies off, or the last 2 rabbits die off, and we get no population, right? So if R is small, we expect this model to predict that and basically tank the population, right? What if the reproduction rate is like 2 or a little bit higher than 2? Well, it'll go up. If we start with few rabbits, it'll grow up. It'll go up. But then because we did introduce sort of that logistic term, the reproduction rate will go down, and at some point we'll hit a stable population, and we'll we'll have, I don't know, 1,025,000 rabbits, right? Whatever it is, right? Some stable population. So let's check if the model actually predicts this. And what we're going to use is, and everybody get their cell phones out because we're going to do this interactive. You ready? And you don't have to do it if you don't want, but if you want to play with it, it's kind of fun. You can, I know we all kind of hate QR codes a little bit, but this will take you to a calculator, and I will also load it up so that I can show you how it works. Initially, it'll look like a mess, and there's going to be a bunch of stuff at the bottom that makes no sense. I'll make sure to explain it to you. Okay, we ready? Okay. If not, cheat off your neighbor or whatever. Okay, so, oops, no, where'd my slide go? Okay, let me just very quickly, I thought I had a link to the slide, but let's see, we can do this way. Holistic map. Oops. I think it's this one. No, it's not that one. Oh, here. You know what I can do is I can actually log into my Desmos account. Sorry, this is taking forever. We can do willamette.edu and okay. Okay. Don't save that and wait, this is not the right thing. That's the reason is I'm not in the right file. I need to go to the right file. This is the one I wanted. Okay. There we go. So this should look something like what you have on your cell phones, and then these let me stop this because it's going to be kind of bonkers. Okay. So this should be sort of what you have at the bottom. And the slider lets you adjust little r, right? So we can go ahead and slide it down to, I don't know, like a half, right? So this would be where the reproduction, oh, no, sorry, R is what I meant to change where to go. Here. Yeah. Oh, it looked like a T from here. Okay, so we can reduce R, say, to a half, right? And then this is how it works. So on the graph, there's this little seed down here, and you can click on it and drag and pick an initial population between 0 and 1, right? So for example, I'll go there. It doesn't really super matter. You can pick your own, okay? And then hit start. And what this is going to do is it's going to go through and look up what the population is at the next step, and then start again from wherever the population. So for example, here the population would be there. Which is, like somewhere around a half. So then it would pick up half, and then it would look up there, and it would kind of keep going like that. So let's let it run. And before I do that, oh, sorry. No, yeah, I did mean to move R, which was up here. Yeah. Okay. Okay. So where is my start? Okay. So let's go ahead and start it. And at the bottom here, what it's going to do is it's going to plot the values that come out just one after another. So we hit start. Oops. Sorry, this is. Is it? Oh, it just went really quick. Here, let me do something. Let's make R a little bit bigger because basically this just tanks the population almost immediately. So let's make it like 0.9. Close enough. And then stop it and then hit reset to seed to start it again. And let's see what happens. So here's what happens. We see that the population basically starts off high, but then tanks to 0, right? And slowly it approaches 0. If we keep going, you can see these numbers just tick down to 0. Okay, so our prediction was great, was good, right? The reproduction rate was low, the population tanks, right? Let's stop that and increase R to somewhere around 2. Okay, and we'll pick some other number and reset the seed and then hit start. And then what we find is the population sort of quickly rises and then hits the stable value of 0.5. Okay? So 0.51, right? Let's use a different seed, so start with a different population. So now we start with a population that's sort of too high, right? The stable population was like 0.5, and we're gonna start a population of like 0.9 or 0.8 or something like that. So let me reset the seed, and then hit start. And if we let it go, population initially drops, but then picks back up, and we get a stable population of 0.51 again. Right? So it's sort of independent, and if you play with it on your phone, what you'll find is that it's sort of independent of what initial condition you pick. As long as it's between 0 and 1, this thing will just go to 0.51 if R happens to be 2.06. Okay? Okay, so that was the results of the model are maybe sort of satisfying that the model did what we predicted and that it sort of seems to make logical sense, but they're not that exciting, right? Like, you could have told me this without doing all this math, right? Y'all are smart. Okay, so let's see what happens as R increases. Any guesses if we keep making the reproduction rate higher? Oh, you actually tried it, okay. Well, like one naive thing would be just like the stable population is higher, right? Or maybe it reaches the stable population more quickly, right? Because you just hit the carrying capacity faster, right? That would be one possibility, right? It's maybe not super obvious, but we expect to be something reasonable, right? Something that makes sense, right? But it turns out that the rabbits are a little bit wascally, right? And so let's try the following. So let's try setting R to somewhere between 3 and 3.4. So 3 and 3.4. And I'm going to have to hop off here and do the thing here. So 3 and 3.4, let's say 3.2 or 3.13, right? And I'm going to just pick some seed somewhere random, reset the seed, start, and look, it just jumps up and down, up and down, up and down. Sorry, I'm moving the mouse a lot. Jumps up and down, up and down, and down. So there's no longer a single stable population. It actually turns out the population alternates year to year. One year you have a smaller population, the next year you have a bigger population. One year you have a small population, then the big population. Okay? And this is robust to changing my initial populations, right? So like if, for example, I go to a population like here and start it again, initially it might look a little bit different, but I still get the exact same alternation between two stable populations. Okay? All right, let's try another one. Between 3.45 and 3.54, that's 3.45 and 3.54. So 3.5 would work, I guess. Okay, there we go. And I'm going to stop this and reset my seed, and then run it. And actually, let me do something for visualization here. There's this parameter L, which it basically says how many dots it'll point before it cycles back and starts over. So I'm just going to knock this down to, I don't know, 30 or something, so they're spaced out a little bit more. Okay, so. Okay, so now it's kind of settled down. And notice what happens here. It turns out we actually now have 4 different stable populations, or not stable populations, but 4 populations that we alternate between, right? We have small population, let's start from the bottom, right? So we have a really small population, followed by a sort of high population, but not the highest population, followed by a sort of low population, but not the lowest population, followed by the highest population, followed again by the lowest of all populations. So now we have 4 different states that are alternating year to year. Okay. Let's do one last one. Between 3.55 and 3.56. So I don't even know if you are able to do that on your phones, but I can type it in here. So between 3.55 and 3.56 would be like 3.54. Oops. Let's see. 5, 4. And, oh, I have an extra period. Okay, so I'm going to reset my seed and start it off. And eventually it kind of settles into this pattern. This one's a little bit harder to see, but it turns out there's 8. So like if you look at this lowest point, and let me maybe zoom in, see if we can maybe make it, let me get, maybe 3. Oh, what's it, 554? Let's rewrite that. Yeah, okay, let's do that and let it run. Okay, I'm going to stop it there. Okay, so now notice that if we start at the very bottom right, we have this, then that, then that, then that, then that, then that, then that. But notice that this and that aren't the same, and this and that aren't the same, and actually this and that aren't the same, and this and that aren't the same. So there's actually 8 different populations that you cycle through over and over, right? And you can imagine, what would you imagine if I increase R a little bit more? Now that we've seen sort of a pattern. So we started with one solution, with one possible population. Then we started with 2, then we got 2, then 4. Now we have 8. What would happen if I increase R a little bit more? Well, I'd probably get 16, right? It's just 2, 4, 8, 16, right? And in fact you do, but it's at that point it becomes really hard to tell that they're different. Okay? So interesting, the rabbit populations actually turn out, can't decide where to settle down and sort of get progressively more complicated. And this process is called a period doubling cascade, and the name probably, it sounds a little bit technical, but you can probably make sense of why it's called that, right? It's because we have oscillations with periods that get double each time, right? First it repeats every 2, then it repeats every 4, then it repeats every 8, then every 16, right? One thing to notice is that these period doublings actually happen sort of closer and closer together, right? So to go from one solution to 2 solutions, I had to go all the way from R is equal to 0 to R is equal to 3, right? To go from 2 solutions to 3 solutions, I had to go all the way from 3 to 3.4. To get to 8 solutions, I had to go from 3.4 all the way out to somewhere around 3.5, so that's only a difference of 0.1. To get to the next one, I only really need to change sort of the second decimal place, right? So these period doublings happen closer and closer together, right? And this turns out to be kind of interesting because if you think about it, then what happens if I keep increasing it, right? Well, it turns out, let's do this. Let's just go right above, somewhere above 3.569946, whatever, right? So 3.6 will work, and let's see what happens. So if we do that, and we go to 3.6, 3.62 is fine. Yeah. Oh, come on. All right, 3.6. Yay. Okay. We do that. Now run it. Sometimes it sort of looks like it's almost repeating, but then later, it's not really repeating, right? And in fact, one can show mathematically that it never repeats, which is kind of crazy. And at this point, it's entered a state which mathematically and in physics we call chaotic, right? So chaotic, by the way, does not mean random, because we have a well-determined rule that tells us how to get these numbers, right? So it's not like we're flipping coins and or picking numbers out of a hat, right? There is a well-defined rule that tells us how to get from one number to the next number, right? If I give you one number, you can go to your calculator and give me the next number, right? Ignoring that calculators only can keep so many digits or whatever. But But there's a well-defined rule, it's called a deterministic rule, that says if I have a current state, I can predict the future state, right? So this is kind of interesting, right? Now, so in this phenomenon is called chaos, right? And basically it has a few interesting characteristics. So first off, there's no, once you get into a chaotic regime, there's no repeating pattern. The thing never repeats. Then there's no stable solutions, right? So in the sense you never fall into one population and stay there, right? It looks random, but it's not, right? There is a rule that tells us how to go from one state to the next state. Now, this is totally mind-blowing if you really think about what it means, right? Because it means that you can have a well-established rule, this is a rule that you can plug numbers into and get a result out, yet over a long time, you have no idea what the output is going to be, right? Which is pretty crazy, right? There's one additional thing that I wanted to show you. So here, I basically made the plot that we saw at the bottom in this graph, right? And just did two slightly different seeds, right? So the blue line shows an initial seed of 0.2, and the red line shows an initial seed of 2.00001, right? So I just changed the initial condition by like a fly sneezing in Canada or something, right? Let's see what happens. Well, initially the two data sets look almost identical, right? And so if we follow it, and everything looks the same. And then all of a sudden, boom, they split. Red goes this way, blue goes all the way over here, right? And then from then on out, they don't really follow each other at all. Right? So this really tells us why understanding chaos is important, right? Because it means that if we have a system that exhibits chaos, right, then prediction becomes hard, if not basically impossible, right? We can't predict for short terms, right? So if I know that my initial condition is close to 0.2, well, for, maybe 10 iterations, the prediction's not that bad. But if I happen to miss that fly sneezing in Canada, and really Lorenz posed it as a butterfly flapping its wings in Brazil, then but I like the PNW version better. Maybe it should be like a beaver sneezing in Canada. Anyway, then over time our predictions get super bad, right? And this is in fact why a lot of physical systems and engineered and human systems are unpredictable, right? So it turns out that one can show with different levels of rigor that a lot of different systems can exhibit chaos. So one sort of classic example is the weather, right? And so if you look at weather predictions, they're not bad for tomorrow, right? Like and even intuitive weather predictions are not bad for tomorrow, right? I'm like, oh, well, it's like, 56 out. It'll probably be like 58 tomorrow, and I wouldn't be that far off, right? But if I try to fast forward 2 weeks, it turns out it won't work, right? And that is because of the fundamental nature of the math underlying weather prediction. That's not to say you can't predict averages, and so, for example, climate modeling works, right? But detailed weather prediction doesn't beyond a certain window. And that's why, for example, when you look at the weather predictions, they never forecast out past 10 days, because beyond that, it'd just be like they'd have to have every single last digit in their data set that they're using for prediction down to, every number they use down to like 15 digits. And you're getting this from weather vanes and all kinds of like satellites and whatever. So that you never have that level of precision. So beyond 10 days, they just don't even try. Right? Other systems that exhibit chaos are, for example, the stock market. So there's a lot of people that make a lot of money trying to develop models that can sort of predict the stock market. Nobody can develop these models that predict out forever, right? If you did, then, it'd be like the movie Back to the Future 2, where he goes and he gets the gambling book, the baseball records book, and then travels back in time and gambles on every baseball game for the next 20 years and becomes a billionaire. Anyway, so there's lots of people that make a ton of money and spend a lot of money on very fancy computers and PhDs to try to predict the stock market just a little bit better than everybody else, right? One that's interesting too, it turns out if you look at an EKG rhythm, that also sort of has states that are stable, right, where you have sort of regular beats, right, regular electrical signals to your heart. Now, it turns out that if you go into atrial fibrillation, the signal in the EKG is actually chaotic. So now you can see that the spacing between spikes is no longer uniform, and in fact, it'll appear kind of random. And what that does for your heart is it doesn't, normally what the heart is doing is it's sort of pushing in one direction. If you have different parts of the heart going off at different times, rather than doing a coordinated, they're doing like a, and so your heart can't pump blood, right? And that's when you go into cardiac arrest, and bad things happen. So there are scientists that are sort of trying to understand the dynamics of the heart using these sort of same tools. And then you have other sort of more gimmicky systems. So like you have a pendulum and you attach it to another pendulum. It turns out that exhibits chaos. This is something your grandkids could build. So here we have two pendulums that start off almost at the same angles, and then you see that over time they end up doing pretty different, wildly different things. Okay, so I know I have basically zero time left, so very quickly, let me just show you one last thing. So we can kind of summarize everything that we saw in this thing called the bifurcation diagram. So here, imagine that for each value of r, so r is going to be on our horizontal axis, we look at what the stable populations are. So for example, for small r's, the only imagine this is our number line here, going up instead of sideways. Our only stable population is 0, right? So that's like if I went to this graph and looked along the axis and figured out where I end up here, and then I'm just going to plot wherever I end up, I'm going to plot that in the other graph on a number line that's vertical. So in this case, it ends up down here at 0. Now, if I increase r some more, I end up with a single stable population there. And as I increase r, that stable population goes up. If I go above 3.3, then I end up with 2 stable populations. If I go above 3.4 or whatever it was, or 3.5, I end up with 4 stable populations and so forth. If I go above that, then I end up here where basically it just keeps landing all over the place and there's no place where it consistently lands. And so this is our chaotic region. Okay. One last little bit. Why did my links not save? Okay, here's sort of a fancier version of it. Here's one kind of interesting thing. Notice that even though there's these regions that are chaotic, right, where we just see it lands everywhere, if we increase, eventually we can actually hit a window where there's only 3 stable solutions again. So that total crazy madness that we got in the chaotic regime suddenly goes away, and then we increase again and it goes away. But there's something even cooler, and this is going to actually lead us into the next talk. Suppose we take that graph and then we zoom in here and just look at what the structure. Well, look what happens. We get something that looks almost exactly the same, right? We have 2 solutions that go to 4 solutions to go to 8 solutions, and they get closer and closer together. Eventually you get chaos. And then notice here's another window of 3, right? And so to close this, let me just go to this YouTube video, which is sort of the coolest video ever. And I guess this is brought to you by Red Bull. All right. So here their A is our R, but and they're just going to build that bifurcation diagram that I just showed you. Okay. So, and what they're going to do is they're just going to zoom in, sort of like I did a second ago. I guess they didn't do the 3 band. There's a 6 band, I think, that do. So you zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. And then they zoom into that, and notice there's the 1, 2, 3 again. And then they zoom in again and notice there's the 1, 2, 3 again, and also the 2 to 4 to 8 to whatever. Then we keep zooming in. And keep zooming in, and there's our 1, 2, 3 again. Right, and you keep going. This video goes for a while. Maybe let's, in the spirit. And I guess at this point they stopped simulating. Right, so that's pretty crazy. And so it turns out this is an example of a mathematical structure called a fractal. And so that's where we're going to start next time for the second half. But right now, I guess I can take some questions, and then we can have a little break. There's a question over there.
Do we have time?
Or
I think, can we handle questions at the
very
beginning
end?
of the next section?
Okay, cool. If that's okay with everyone.
Yeah, I think we should take a 10-minute break.
In that case, I might need to, hold on, I think I have it in my Dropbox. Because I didn't throw that on the thumb drive. Okay, so while I boot up the thing, maybe people that need to hit the restroom.
So we'll take a break, come back at 11:15. Thank you.
Okay, let's get in our seats, please. Stop the conversations. Please get in our seats. We're ready to go with the second half. Here's Daniel.
All righty. We ended the last talk by showing you an example of a fractal. And so we saw that this was a structure that kind of repeats infinitely. As we zoom in, we get sort of the same thing over and over and over and over and over again. So this talk, which is called From Landscapes to Lettuce, Fractal Geometry in the Real and Not So Real World, is one of my lectures about fractals that I do with students. Okay, so here is our beloved state of Oregon. And this is for students in the first year, so there's a bunch of like where things are and what the fun things to do in the state are, but you all know these, so I'll skip that. Okay, so we have Oregon, right? Washington to the north, the Pacific to the west, Idaho to the east, and California and Nevada to the south, right? And of course we have the beautiful Oregon coast, and there's lots of things there. One question, how long is the Oregon coast? Ballpark it. 360. 3 something, right? Well, we can do a little bit better if we have a scale bar, right? And so here I have a little scale bar, and let me turn the laser on. A scale bar that's like 20 miles, and of course I could plop one down, that's 20 miles, 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 20, and we get to Astoria. And it turns out I laid down 15 bars, so that tells me about 300 miles, right? So I heard 300s, 400s, right ballpark, right? It's not super accurate necessarily, right? Can we do better? How would we do better? Smaller bars, right? So, okay. So, and keep in mind that 300 number for later, okay? All right, so let's zoom in, right? And so, and doing the whole coast would take forever. So let's just zoom into the north coast, sort of between Astoria and Cape Meares, right? And now we'll use a smaller bar, and then just assume that everything kind of stays more or less the same the rest of the way down, right? So we have 2.5 miles there, 2.5 miles there. This took a while to do in PowerPoint, by the way. And we lay them down, and we get 32 of these little bars, which is 80 miles. Oh, by the way, there was an animation here that I didn't see come up. Oh, yeah, no, here it is. Okay, so notice that the Oregon coast from Cape Meares to Astoria at this scale is measured with 3 bars. So it's about 60 miles, right? So 60 miles at this scale. At this scale, it's 80 miles. Okay, so that's off by third, 33%, right? Let's see if we can do better. So let's look at Tillamook Bay here, which at this scale is 22.5 miles around, right? There's however many bars, 11 something bars around. So we zoom in, and now we do 2,000 foot bars. Again, you all should thank me for all this PowerPoint. There's 98 of these 2,000 foot bars, which comes out to about 37.1 miles, right? So before we had 22.5 miles, at this scale it's 37.1 miles, right? So if we sort of extrapolate the, so we basically underestimated things by 40%. Now, notice we underestimated things by 30% in going from the biggest map to the second map, and then now from the second map to this map, we underestimated by another 40%, right? So if we extrapolate out to the whole Oregon coast, and I had this in the notes that are on the, let me see, because the number's actually pretty surprising. So basically, if we extrapolate this level of approximation out along the whole Oregon coast, we're probably off by about 75% from our initial estimate of 300 miles, and the coast would actually be about 525 miles if we measured it with 2,000 foot rulers. Okay, and so this is an example of something called the coastline paradox. This was introduced in the 50s by Richardson. And Richardson was a pacifist, and he was really kind of interested in how can we prevent wars, or like why do wars start and how can we prevent them, right? And one idea that he had, which isn't like an insane idea, I don't know if it's a super well-baked idea, but it's not an insane idea, is that the likelihood of two countries going to war is somehow related to how much of a shared border they have, right? Which sort of makes sense, right? Like if you share a lot of border, there might be a lot of possible conflicts that come up. If you don't share a border at all, well, I mean, in the 21st century, maybe that's a totally different beast. But, you know, like when it took time to get places, if you don't have a shared border, the likelihood of you going to war was pretty low, right? And so Richardson sets out to test this, and one thing that he looks at is the map of the border between Portugal and Spain. And interestingly, it turns out that he gets different numbers for the border if he uses the Portuguese maps or the Spanish maps. And that's because they were drafted at different scales, right? And so he discovers that coastlines actually depend on what scale you measure them at. And this is called the coastline paradox. Okay, so studying coastlines, like I said, I spent a lot of time doing PowerPoint, so I'm going to do something a little bit easier that is an artificial coastline that we can actually understand. So it's not as complicated as Tillamook Bay. Okay, so let's build something called a Koch curve. And this is a German mathematician, Koch. Anyway, so let's see how we build it. So we'll start with a line segment that is, let's say the length of this thing is 1. Okay, and then what I'm going to do is I'm going to knock out the middle third, and then make a spike that the length of this is 1/3. So that's 1/3, that's 1/3, that's 1/3, and that's 1/3. Right? So the length now is not 1, but 4/3, because there's 4 segments of 1/3. Okay? All right. But that doesn't look like a coastline. So now what I'm going to do is I'm going to knock out the middle third of each segment and put a little spike that's 1/3 the length of each little segment. So now we do this, right? And so now this little piece is basically 4 times 1, or it's 4/3 of 1/3, right? And the same for each one of these. And we can keep doing this, like, you're right, like Koch had lots of time because he was living in like the 1800s, and so you can keep doing this, right? And now you get something like that and something like that, and I think that's really kind of, at that point, it looks a little bit, at least structurally, more like a coastline, right? There's a lot of like little inlets and stuff. It's a little too structured for a real coastline. We'll get back to that later. But at least it has a lot more structure, right? And really what Koch studied was what happens if you do this an infinite number of times. So you keep doing this, right? And so this kind of brings us back to the idea of repeating structure at, like, you can zoom in forever and you keep getting the same thing, right? Notice that if I zoom in here, this is just a small copy of the whole thing here. Okay? And also notice that there's another important thing here. We built this thing that's a very complicated curve with a very simple rule. Knock out the middle third and make a spike with 2 segments that are 1/3 of the length of each segment that we cut out, right? So that kind of harkens back to before, right? We had this really simple quadratic equation that looked like a parabola. It was boring, but it ended up giving us chaos, right? This is sort of something similar, right? We have this very simple set of rules that we can follow and build this thing that will turn out has kind of mind-blowingly weird properties. Okay, so here's a question for you, and let's just see what you think. Does the Koch curve have a well-defined length? That is, could I say if I want to travel from one end of the Koch curve way here on the left and at the other end of the Koch curve on the right, is there some number of meters or centimeters or whatever that I need to travel? It seems like there should be, right? I'm going from A to B, right? And so it seems like there should be a well-defined length between those 2 points if I follow that curve, right? Okay, let's see if that's true. Okay, so let's look at the length of these figures as we add more and more detail to them, right? So the first one has a length of 1, right, by definition. The next one has a length of 4 segments of 1/3. And I'm going to write this in this weird way, which will become useful in a second. But I'm going to call that 4/3 to the 1 power, which is just 4/3. Okay? As the next step, now I have 4 pieces that are 4/3 long, right? So the length, and if you don't follow the math since we're a little bit short of time, I'm not going to like worry about it too much. But what it turns out it comes out to 4/3 squared, right? Then 4/3 cubed for the next one, 4/3 to the 4th power for the next one. Now, what happens what happens if I do this an infinite number of times? Well, 4/3 is a number greater than 1, right? What happens if we take a number greater than 1 and multiply it by itself an infinite number of times? Forget 4/3, let's do 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, right? Dot, dot, dot. What happens if I do it an infinite number of times? I get infinity, right? So notice what I'm telling you here, right? The length of these curves, as I add more and more detail, increases by a factor of 4/3. And if I do this an infinite number of times, what's the length of that curve? Infinity, right? So this is an interesting thing because it's a curve that has an infinite length, yet it doesn't go out to like infinity, right? But the distance that you would have to walk along that curve to go from one end to the other actually goes to infinity. You can't actually do it and even if you walk the entire lifetime of the universe along that curve, you never get to the other end. Assuming, of course, that you could walk at infinitesimally small scales. You're like a micro ant or something. Okay, so that's one kind of crazy thing about this fractal curve here. Okay. Here's another, this next one is going to require like a little bit more math, but the payoff is good, so stick with me. Okay, so here we have a line, and I can't draw it infinitely thin, so we'll call that a 1D line, right? And then we have a square, which we say is a 2D shape, right? A cube would be 3D, right? What do we say what do we mean when we say a line is a 1D shape and a square is a 2D shape? Yeah, that's a good point, right? One has a length, and that length could be infinite, as we've seen, but that one has length, right? The other one, on the other hand, has both a length and a height, or a width and a height, right? So we need like 2 numbers to represent that. It has an area, right? The 1D curve doesn't have an area, right? What if I give you just some generic shape, and I ask you to tell me if it's 1, 2, or 3, or whatever dimensional? How do we do that? So what I'm going to introduce to you right now is a way to actually calculate the dimensionality of an object, right? So assuming we didn't know it is 2D, can we do a calculation on that shape that spits out 2, right? And if we do it on the line, it spits out 1. Okay? All right. Do you have anybody that learned to do calculation on a slide rule here? I know there was at least one. All right, so y'all are going to be happy with this. Okay, so And by the way, is the coastline a 1D curve? So if we track the coastline, define in some way, right? Like maybe the average level at which the water is over 100 years or something. We define that curve as our curve. Is that a 1D curve? I mean, it should be, right? Like, it doesn't have area, right? Okay, so let's see if we can run our calculation on, once we figure out how to do the calculation, we'll go back and apply it to the coastline to see what happens. Okay, so I'm going to introduce you to a concept called the box counting dimension. And here's how it works. What I'm going to do is I'm going to start off and figure out how many boxes of a given size I need to completely cover my curve or my surface, right? So in this case, if I use a box that has a length of 1, I only need 1 box to completely cover my little line segment, right? So at a length scale of 1, I only need 1 box, right? Now, if I make my boxes sort of half as big, I need 1 and 2 boxes. So at a length scale of a half, because now the boxes have a side length of a half, I need 2 boxes. At a length scale of a fourth, I need 4 boxes, right? At a length scale of an eighth, I need 8. Okay, so what's the pattern here? What's the relationship between the size of my box and the number of boxes that I need? 1 over, right? The reciprocal, right? And mathematically, we can write that thing down as n to the 1 over, n is equal to 1 over L, right? And for reasons that will become apparent, I will write this as 1 over L to the 1 power, but that's just 1 over L, okay? All right, now let's do the square. Okay, at a length scale of 1, I need 1 box. At a length scale of 2, now I need 4 boxes. At a length scale of a quarter, I need 16. At a length scale of an eighth, I need 64. Okay, this one's a little bit trickier. Anybody know what the pattern is? 1 over the length squared, right? So the number of boxes that I need is 1 over L squared, right? Okay, now we can do it for a cube. Now we're actually going to have to use 3D boxes, but, and I won't belabor you with the animations, but it goes 1 to 1, 1/2 to 8, 1/3 to 27, 1/4 to 64. But this one's a little trickier. It turns out it's 1 over the cube, right? So we can write that as n is equal to 1 over L to the 3rd power. Okay, so let's summarize everything we did. So for a line, the number of boxes that we needed was a 1 over L to the 1st. For a square, it was 1 over L to the 2nd. For the cube, it was 1 over L to the 3rd, right? And if we call the dimensionality of the object D, where does D come up in these equations? It's the exponent, right? Like that to the 1, to the 2, to the 3. Generically, we get that the number of boxes that we need is 1 over L to the D power. And depending on what shape we have, we're going to get, once we do take our data table, we're going to get different values of D, right? And okay, so that's our general idea. Okay, so this is where the slide rule and some high school trauma comes out. But bear with me. So how do we go about that? Because what we're going to have is we're going to have data of the number of boxes and of the size of the boxes that we used, but we want to extract that D, right? So everybody get ready. Let's do some logarithms. So we can take the logarithm of both sides, and if you don't follow this, don't worry about it. We'll get to a more qualitative argument in a second. And then we're going to go back to our high school textbooks and remember, as you all I'm sure do, that the logarithm of a to the b is equal to b times the logarithm of a. And that gives me this, right? So that d can go out in front of the log. Okay. Now I'm going to define 2 new variables, so I don't have to work with these logs. I'm just like, I don't want to see those log signs. So I'm going to let y be log n and x be log 1 over L, right? So I'm just replacing log n and log L by y and x. And I get an equation that looks like this. Okay, now notice this equation is the equation of a line, if you remember, right? Basically it says that one variable is proportional to the other, and they increase by the same amount if I increase them by the same amount, in the same proportion if I increase x, y increases in proportion with a proportionality constant d. right? So for example, if D was 2, like we had in the first example with the rabbits, right? If D was 2 and X is 2, then Y would be 4, right? If D is 2 and X is 4, Y would be 8, right? And we saw that that gave you a sort of population that grew linearly forever, right? Okay, so this is an equation of a line with a slope of D, and that measures how steep, or D therefore measures how steep or not steep the curve is if we plot X and Y on a graph. Okay, so let's do that. So basically what I did here was I took each one of these tables that we had way back here. I calculated the log of each column. So I threw it into my Excel sheet and I said, calculate the log of 1, of 1/2, of 1/3, of 1/4, put that in one column. Then calculate the log of 1, 8, 27, and 64, put that in another column, and then plot the two, one versus the other. And then I told it to fit a line and tell me what the slope of those lines are. And so here's the data for the line segment. And notice the data falls on this nice line in this log-log space. And furthermore, the coefficient out front for the line fit is 1. So this tells me that the dimension of the line is 1. Okay? If I do it for the square, I get this orange data set. And when I try to figure out what the slope of that line is, I get a 2. So that tells me that the dimensionality of the box, of the square, is 2, right? When I do it for the other one, it's a little bit hard to see, but I get a 3, right? So that tells me that the cube is a 3-dimensional shape. So our technique works, right? All I have to do is I have to make these little boxes of different sizes and count how many I need to cover the shape, and just take a bunch of data and then take the log of both data sets and plot them, measure the slope of the line, and that gives me my dimension. Okay? Okay, so rather than going for the Oregon coast, because again, it's too hard, let's do the Koch curve, right? And rather than using square boxes, I'm going to use rectangular boxes just because of the shape of the thing, but the argument still works, right? So at a length scale of 1, I need 1 box. At a length scale of 1/3, I need 4 boxes, right? Because there's 4 copies that are 1/3 as big as the original thing. At the length scale of 1/3 of that, which is 1/9, I need 16. At a scale of 1/3 of that, I need 64. And I can keep doing this, right? Now, this one, if you stare at it, you'll never get it. I can't imagine there's anybody in this room that can tell me the relationship between these two data columns. Let's see why that is the case. Well, what do? We take the log of both things, we make our plot, we fit a line to it, and then we measure the slope of that line. Let's see what happens. Well, here's our Koch curve. It lies somewhere between the line segment and the square. So the dimensionality of the Koch curve is not 1, it's not 2, it's 1.2619 and change. So this is where the name fractal comes from. It's because these objects actually have fractional dimension. It turns out that if you define, and there's various ways to define the dimensionality of an object, this is just one way to do it. You get non-integer numbers. You don't get 1, 2, or 3, or even 4, or 5, or 6, or 7. You get 1.2619, 7, 8, 2, 3, 2, 5, and then it goes on forever usually. So this is kind of wacky, huh? All right, how am I doing on time? Let's see how fast we have to go. Okay, we got some time. Okay, so this is pretty cool, right? So we learned 2 wild things about the Koch curve, right? We've learned that A, even though it goes from A to B, it has an infinite length, right? Without ever having to go out to infinity, we could draw it out, well, not by hand draw it, but we could generate it on a piece of paper and it would stay within the piece of paper, but yet it would have an infinite length. And then B, that its dimensionality is actually 1.2619, right? So it has a fractional dimension. Okay, now can we do this with coastlines? I can't, but people have taken their sweet time and done this. And so it turns out you can sort of see which coastlines are going to have higher fractal, are going to be less close to a dimensionality of 1, right? So the west coast of Great Britain, right, of course, is this jagged mess, right? And so its dimensionality actually comes out to be about 1.25, right? So it's not that far from our Koch curve in terms of dimensionality, because it's very jagged, right? Australia, a little bit less so, right? There's sort of a lot of smoother areas, right, that aren't jagged cliffs, right? So its dimensionality is about 1.13. South Africa, turns out, has a really nice, even thing. That looks almost just like a regular curve that we could draw with a pencil, right? And so it has a dimensionality of about 1.02. So it's almost like just a regular curve, right? Okay. Turns out there's other fractals in nature, and we could, if we wanted to, we could go and try to measure dimensionality. So for example, something like lightning will have structure at all kinds of different scales, and we could map out, we could generate little 3D boxes and figure out how many we need to cover it and do that whole thing. And at least up to some level, obviously at some point we zoom in enough to where we're talking about individual atoms and whatever, and that doesn't break, but we can estimate the dimensionality of these objects, and it turns out these will all have fractal dimensions. So if we look at like a tree and then a branching of a branching of a branching of a branching, there's many generations of branches, and if we look at the structure overall, it's kind of fractal, right? Okay, now it turns out that you have a fractal in you as well. So if we think about breathing, right, you bring air into your lungs, and then that air gets brought up near your blood, and then you get oxygen going into your blood, CO2 coming out of your blood. And notice that of course depends on how much surface area you have, right? If you want it to be really efficient at transferring oxygen, you don't want to be transferring over like a little tiny patch. You want like a big exchange area so that you can move a lot of oxygen, right? Because ultimately what's going to happen is the oxygen from the air has to like hit some surface, go through it, end up in the blood, and the CO2 has to go through some surface, hit it, and go out. So you want a big area, right? Well, the problem is that we are not giants, right? We are relatively compact. So our volume is relatively small, but we need to pack in as much area as we possibly can into our bodies to do this gas exchange, right? So what's the trick? Well, our lungs have fractal structure, right? So it turns out that if you took the total surface area that's packed into your lungs and spread it out flat, you actually have about the surface area of a tennis court packed into your chest. Or what is it, like 4 pickleball courts? In 2026, tennis out, pickleball in. Okay, so even you are fractal, right? And there's other examples of fractal structure in your body as well. But lungs are sort of the classic example. In fact, you can use this for these ideas that I introduced you for medical purposes as well. So you can do scans of your airways and then basically try to estimate the fractal dimension of those airways. And so here you see this person has an airway fractal dimension of 1.9. Right? And then as their lungs sort of get worse and worse, right, the fractal dimension drops to about 1.09, right? Similarly, here you have sort of individuals whose airways are narrowing, and as that happens, they lose sort of a lot of the little smaller structures around the bigger airways, and you can also see the fractal dimension drops from about 1.7 to 1.4. So it turns out that by measuring this airway fractal dimension, you can actually sort of correlate it to mortality risk in lung disease. So this stuff isn't just like wacky math that I'm talking about. Okay, let's see. Oh, no, we're good. Okay. Okay, so one problem with the Koch curve, though, if we're talking about, say, lungs or some other natural structure like the ones I showed you back here, right, is these things aren't completely regular like the Koch curve was, right? Like this, like a tree, like it's not like 3 and then 3 and then 3 and then 3, right? It's kind of like sometimes 2, sometimes 3, whatever. So can we do a little bit better in modeling those? It turns out we can. So the example of the Koch curve is what's called a deterministic fractal, right? There's a well-defined rule that takes you from one generation to the next until you get to the Koch curve. But we can also do a random fractal. So basically, at each step, what we do is we flip a coin, and if we get heads, we go make the little spike down, for example, and if we get what did I say, tails, then we make the little spike up, right? So at this point, we are actually introducing an element of randomness into our generation. For example, if we do it this way, and I actually messed up the first generation in this animation. I need to fix it, but didn't happen last night. Okay, so we're going to flip a coin, and let's say we got heads, and so we'll knock out the middle third and make a spike up, right? Then we'll flip a coin, we got heads, we'll make a spike up. Then we flip a coin, we get tails, we make a spike down. And now we can kind of keep doing this. So now for the next generation, we flip a bunch of coins, and we do. Right? If we do this a bazillion times on a computer, and not with me animating it in PowerPoint, you actually get something that looks like this, right? Now, if you stare at this, it's still mildly reminiscent of the Cock curve, but it looks a lot more like that coast of Great Britain, right? So these so-called random fractals sort of give you more natural-looking fractals than the very structured ones that you get from deterministic rules. Okay, we can also make fractal landscapes, and so this is a 2D, well, not 2D, it'll turn out to be more than 2D, but 2D-ish fractal. And here's the process that we'll do. We'll take a triangle, and then we'll draw a triangle inside of it that goes from the midpoint of every side, right? So we split this side in two, make a point there, split this side in two, make a point there, split this side in two, make a point there, and then draw a little triangle between them. And then what we can do is we can basically distort the remaining two sides. So the initial triangle in the middle stays the same, but then the other things get sort of tweaked a little bit randomly. Then we do it again for each triangle. Of the outer triangles, we inscribe triangles that's built by the middle points, and then we tweak. And then we do this a bazillion times. What does that last one look like? It looks like a mountain range, right? Or landscape, right? So it turns out that this is a really easy way to generate something that looks kind of like a landscape, right? And in fact, this is used in video games and movie animation, right? So this scene here is basically several different fractals that are different rules. One that builds kind of landscape, one that when you run it actually builds things that look like grass. They're overlaid on top of each other, and then they add lighting, and so this is actually built with fractals. Now, here's another one. Right? So they've built, again, a landscape, and then there's some other fractal with the different rules than the ones I explained that generate things that look like trees, right? Now in video games, and maybe this is more for like the grandkids, I imagine, but why would you do this in a video game? Well, the reason is that if you wanted to store the information of where every single tree is on your computer and like what it looks like, whatever, that's going to take up a ton of memory, and you just can't fit it on your computer, right? On the other hand, generating the fractal is pretty easy. You just give it sort of, you have something that will generate numbers that appear to be random, but you can actually recreate. So the logistic map would let us do that, right? We could use it when it goes to chaos. We just plug in some initial seed, and then it will always give us the same sequence of numbers that look random but really aren't. And then use that to, so I say when you get to level 3, the seed for the logistic map is 0.6. And then run these 3 fractals starting from 0.6, and then the computer can do, or the PlayStation or whatever, can run the calculation super quickly, but it doesn't have to store all this information, right? And so that's one place where these fractals are useful. Okay, the last little piece, and then we will have time for questions. This should take just a couple minutes, is about fractals at the grocery store. Okay, so here is an eggplant leaf. And let's just look at the edge here, right? Do we think that it's like super fractal, like the coast of Great Britain, or is it like, would its dimension be sort of closest to 1? Yeah, it's South Africa, right? Like even if we get like 1.02, we're not going to get like 1.5, right? Now, being evil scientists, and this was work done in my PhD advisor's lab, one thing that we can try is putting growth hormone, but just on the edge, not on the whole leaf, so the whole leaf doesn't grow. It's just the edge gets longer while the rest of the leaf stays more or less the same size, right? Well, if we do that, the perimeter of the leaf grows really fast, but since the area doesn't grow, the edge has to go somewhere, right? Where does it go? It pops out of the plane, and now we get wiggly edges, right? So this is about after 10 days of applying the growth hormone. We can keep doing this. So here's after 12 days. And notice you're starting to pick up some additional little curvies, right? And we get more and more fine scale structure as the perimeter gets longer and longer and longer. But remember, we have to fit it in a finite amount from like A to B on one side or the other of the stem, right? So this is sort of the same problem that we ran into with the cock curve. We're trying to add more and more length while keeping the two ends fixed, right? And so something has to happen. In the case of the cock curve, it pops off and makes a cock curve, right? In this case, we get wiggles on the edge, right? Here's 14 days. So now you can see there's sort of structure on structure on structure on structure, right? And so this is kind of interesting because it basically tells us that how wiggly the edge of a leaf is tells us something about how that leaf grows, right? It tells us that if you have a really wiggly edge, then the perimeter of the leaf grows, the growth of the leaf happens mostly at the edge, the border of the leaf, and the middle stays more or less fixed, and as the perimeter gets longer, it pops out of the plane. If the leaf sort of is just kind of flat and has a nice smooth edge, then the leaf sort of grows from the middle out. And so if you go to the grocery store and you look at all your different leafy greens, you can sort of learn, you can tell your grandkids about how those leaves grow by looking at the edges. Wiggly, the perimeter grows faster. All right, so I'll stop there and I'll take questions about either talk.
This is Gwen Ellen, and I'm just going to start by asking you, how do your students react, or how much do you have to explain when you talk about punch cards and slide rules?
Yeah, they have no idea. I tell them all, but they are fascinated about it, and they actually like that slide about Margaret Hamilton and I forget her name, Faber. Yeah, but they really like it, but they don't know anything about it. Fetter, yeah, thank you.
As a math teacher, I'm just in awe of the teaching tools you have now. We use logarithms and logarithm tables and slide rule when I started, I hate to admit. But I could give a pretty good history of computation. But the idea that you can take your cell phone and take a picture of that QR code, and you've got the simulation going on mathematically on your, it just wasn't imaginable. Wasn't imaginable.
I mean,
for me.
it wasn't imaginable when I started teaching like 12 years ago. I guess while Gwen Ellen passes the mic, I actually have both of my uncle's slide rules from when they were in grad school, and my uncle Albert he's very proud of this. It was the first model that had Teflon sliders on it, so you could like slide it faster, and he knows to the date when that model came out, and then also when the first HP calculator came out, and he bought it the day it came out. And I think he still uses it, or before he retired, he still used it for his engineering.
My name's George. Question about that dimension idea. The numbers were between 1 and 2, but then when you went to lungs, which are three-dimensional, I was kind of expecting that number to be between 2 and 3. And are there some dimensions beyond the 1 point something?
Yeah, no, you can have 2 point something. I think the reason that this animation is going to take too long to backtrack through. I think the reason that the airway dimensions is because they're looking at the 2D images and just looking at those curves. They're not looking at the overall surface. So if you did a 3D reconstruction of the lung, then the dimensionality of the surface area of the lung would be 2 point something, right? Because it's sort of like an area that's not quite a volume, but it has area, right? So here, I think it's just because they're looking at maybe the perimeter of these shapes that come out in the 2D scan. And so that's somewhere between 1D and 2D.
Hi, my name's Mark. As you were giving the fractal presentation, I was thinking about the concept of space-time and distance. That this fractal math could be used to help understand the distance between far-off objects, correct? Because gravity affects that distance that light is traveling?
So it doesn't usually come up in that context because in general relativity, the space-time is smooth, and so it doesn't really end up having sort of infinite levels of detail. Like if you zoom in enough, it just looks flat, and that's actually sort of a foundational axiom of general relativity, is that locally, if you zoom in enough, space is flat, or space-time is flat. And so you can't really have fractal structure if you have something that's perfectly flat. It's like, it would be like trying to make a curve, if you zoom in on the car curve, right, no matter how much you zoom in, you still have more structure. If you zoom in on a circle, if you zoom in enough, it looks like a straight line. You don't have an infinite layer or infinite layers of structure, so it doesn't really come up in that context, but it comes up in a lot of other physics contexts.
I'm David. Going back to the logistic map way long time ago, is there a chance that that's showing us why one child, one family in China didn't work?
I mean, I think that question is a little bit more complicated than this map, but there are people that develop more complex population models that would do this kind of thing. The logistic map, it turns out, doesn't work super well for rabbits. Really, the types of organisms where it works pretty well is like bacterial colonies, where you have like billions of individuals, and but yeah, those population models can get pretty complex. Like, for example, we didn't add geography to this at all. Like, the rabbits were all just on an island, and we didn't care about how they were distributed. We didn't have predators. So human population modeling is pretty complicated, right? Because you have economics, you have all these things you need to bring into it, and it gets. But yeah, overall, like once you get into sufficiently complicated models, you can make predictions like, this particular policy will send the population or the economy to zero. Economics uses this kind of modeling a lot too.
Hi, I'm Bonnie. I might have missed the entire point of this, but I'm trying to understand with Zeno's paradox, right? Isn't everything infinite length? Like,
okay, yeah. So, well, Zeno's paradox, it doesn't tell you that the distance is infinite, right? It tells you that if you're advancing in progressively smaller steps, you never get there, right? Which is a slightly different statement in the sense that. For example, a line segment has a well-defined length, right? I can take a ruler to it and measure it, and I get a length. And it doesn't matter if I use the smaller ruler, I will still, a finer ruler, I'll still get the same length, right? In a fractal, that's not the case, right? So.
But isn't it kind of infinitely dimensionable? Like you just keep.
Right, but what. Yeah, so Zeno's paradox is, it's a little bit different, and for those of you who aren't familiar, right, is the idea, Zeno proposed, the Greek philosopher, right, that like, suppose you have Achilles and he's running towards some goal, right, and there's 10 meters. If he first travels half, then he still has to travel the remaining half, and then he travels a quarter, and basically each time he gets closer and closer, but he can't ever actually reach it, and it's sort of what Zeno proposes. That all gets resolved in the calculus, in the mathematics of calculus, and so you actually find that, in fact, he does reach it. But this turns out to be somewhat different, and I wish I had a better answer. That's sort of super satisfying, I don't think.
So this, the 1960s and 70s, this is a very nascent, very young science. What are the leading edge? What's the next frontier in discovery of these applications of fractal math?
Fractal math, I haven't followed that much. In the dynamical system stuff, I mean, basically modeling all kinds of stuff. It's the kind of math that applied mathematicians and physicists use all the time. And so basically you make the models more complicated. And sometimes higher dimensional, right? So like, for example, if you add predators to the rabbits, then you have to keep track of two populations, and then you can imagine doing entire ecosystems. The big hot one right now is running these models on networks. So the idea that maybe some parts of the population are connected to others, and once you add that connectivity, the model gets a lot more complicated, because now it's not, the way we did it, it's sort of all to all. Everybody just has babies with everybody, and it's all kind of mixed into a rabbit island. But if you talk about rabbit A can only have babies with rabbit B or C, but B or C can only have rabbits B, C, or D, and like you add that whole network structure to it, things get incredibly complicated and nobody really knows how to work it. And of course, it's kind of key in this area, right? If you think about how information propagates through Facebook, right? We're not all connected to everybody. We're connected in these nodes with like bubbles, right? And so that's an area where it comes up a lot. And then all this math sort of ends up being relevant.
Okay, we have time for one more question, and then Mark Kendall has one announcement to make.
Okay, I think you may have already answered. I was going to ask you about other dimensions, and what I was thinking for landscapes is adding time, adding a fourth dimension, but you already said you can make more dimensions, so I think you answered my question.
Okay, well, yeah, of course you can make the landscape time dependent, right? Like you can imagine waves on the ocean, right? The topology changes, or topography changes over time, and that's totally allowable. Yeah. Okay, well, I gotta run because I have a class, but thank you all for listening. And I heard there's a field trip. Have fun.